Welcome to this last tutorial that I plan to be doing. This is a somewhat different topic to the previous tutorials, which were all using finite element methods. In this case, we'll be using finite difference and finite volume methods. The tutorial itself is based on two tutorials from the book, tutorial 13 and 14, where I do give quite some detail, at least, on the methods used and the theory for computational fluid dynamics. I won't go into such detail here, but hopefully it will be sufficient for you to get an idea of how these analyses are performed. The presentation is split into 4 parts. First of all, I'll quickly give you an introduction to the theory. As I mentioned, this will not be in very great detail, but hopefully sufficient. I'll then move on just to suggest a finite difference example that you could try yourself using a code like MATLAB or open source softwares like FreeCAD. Then I'd like to explain how you install OpenFOAM within FreeCAD. This is not such a straightforward process, so I will show you that. At least it's not so straightforward on Windows. And then I'll also be showing you a little bit on the post-processor that's used and the installation of this. The post-processor is ParaView. We don't use FreeCAD for post-processing results. We use ParaView. And then finally, I'll move on and show you an example, a fairly simple example using OpenFOAM in FreeCAD, of course with ParaView to illustrate the results. I just want to clarify the 2 types of techniques you could do for flow of a fluid through some kind of a medium. We could either use field equations or we could use CFD type techniques, but each is only suited for certain applications. So first of all, field equations. We have indirectly already done this. In tutorial 2, we used finite element representations of the Laplace and Poisson's equations to predict heat transfer through a body. You could replace the temperature boundary conditions with pressure, and you could replace the conductivity with permeability, and then you would use exactly the same algorithms, exactly the same modeling and analysis techniques to do the prediction of fluid flow. The results would be shown, or are shown on this diagram at the bottom here. These would be streamlines. They run more or less parallel to each other, and you could overlay so-called isopotentials of pressure. So for example, this line here is an indication of a contour of constant pressure. The gradient between these is an indication of the speed of flow. So for example, that would be an isocontour, an isopotential for pressure here. There would be other ones that would do something like this, and you would have more intensity of these isopotentials in this region and here, indicating faster flow here than this region, and so on. This is only suitable for inviscid liquids, that means liquids that have no viscosity, and for very slow flow of viscous liquids. That would then give you, such an analysis would give you a reasonable prediction for these types of fluids. It will not predict any separation, and that means, for example, you will have a streamline that will come right round here and then come off in this direction. There will be no possibility for separation here, and you have no chance to predict such things as turbulence. It simply is not possible from these algorithms. The flow is called irrotational because there is no chance for rotation effects causing this turbulence. In effect, the streamlines always intersect these isopotentials at right angles. On the other extreme, we have this CFD technique, which uses a very different physics to model the the problem. We use the Navier-Stokes equations. These contain mass, momentum, and energy equilibrium or conservation. It can predict eddies, turbulence, separation, and so on, as we see here. And it is for fast flow of viscous liquids and viscous gases. And it is the viscosity in these materials that tends to cause this turbulence effect. The fluids can be either a gas, which can be incompressible, but usually we would consider it as compressible, or it can be an incompressible liquid. There is a kind of magic number called the Reynolds number, which decides whether or not you should be using this technique or this technique. And that is given by this formula here. And that's essentially a ratio between inertia forces, which are caused by the speed of flow, and the viscous forces, which are dependent upon the viscosity of the liquid. If this Reynolds number, which is dimensionless, is less than about 2,600, you should be using a field equation method. If it's above about 4,000, you should be really thinking of using this CFD technique. And as I say, between this sort of 2,600 and 4,000, there is a transition phase where it could be a slow flow type analysis with field equations, or it might become a problem that involves eddies and turbulence. This is just a few miscellaneous points I'd like to mention. There's some examples at the top on the left there of applications of CFD analysis, basically flow around obstacles, flow within pipe systems, airflow around structures, cars, aircrafts, and so on, heat exchangers, and there are some more exotic type applications such as blood flow in parts of the human body and so on. But there are many applications, in fact. They're all based on using these Navier-Stokes equations, which I will briefly be mentioning. These are conservation equations for continuity, that means mass conservation, also momentum conservation and energy conservation. In the solution we have independent variables. In this case they are positions x, y, and z, and time. And we have dependent variables, which would be velocities, UVW, pressure, density, and temperature. Density and temperature is really for gases and problems involving thermal analysis. Just one point to mention there, U, V, and W is the normal nomenclature for this type of discipline, These are velocities here. In the previous work, in standard finite element analysis, we would regard those as displacements. The three main techniques that are used are either finite element, finite volume, and finite difference. I will mention a little bit on the finite volume and finite difference techniques a little later. And you can use the method for either steady state or transient analysis. If you are interested to read more on this topic, there's one reference at least at the bottom there. You'll find PDF files and extracts of teaching material from J.D. Anderson on the web. It's a very good document and well worth looking at. There are two ways we can try to characterize the flow of a fluid. The first in the upper left there is a so-called non-conservation approach, in which you characterize the liquid as it is moving with the flow of the fluid. So we can see two times here, T1, T2. This will have a certain velocity. Here it will have another velocity. And the various equations are characterized with respect to this flow. The other approach is called a conservation flow. In this case, if we have a control volume, we assume that it's fixed in space and we try to characterize the flow of the liquid as it moves through this control volume. Sometimes this is called a Eulerian approach, and this is called a Lagrange or fixed reference frame approach. We can characterize the flow as it's moving, and I've showed this in the bottom left. It's described using something called a substantial derivative, or a total time derivative. If you have, for example, density, and it has in this control volume, and we have a position x1, y1, z1 at time t1, this control volume may move to a new position x2, y2, z2 at time t2. There's a velocity vector here representing the flow at this particular position, and we have another velocity vector here representing flow at this position. These velocity vectors would be u, v, and w in the x, y, and z direction. So, for example, if density is a function of position x, y, z, and time, then you can use a chain rule of differentiation, and you can come up with a so-called substantial derivative expressing how this change in density with time, total change in density with time, is taking place. Now, I've not derived it here, but it's fairly straightforward. You'll find this in the book on Anderson, the references from Anderson. It comprises of the change in density with time. So this is called the local derivative, plus these convective derivatives. So this local derivative may be due to, for example, the constitutive law that's being used, and these will be due to the movements that are taking place. So we have in this particular case, it will be the velocity in the x direction times the change in density with respect to x, and you have similar functions here for the y and the z directions. That can be expressed in this simplified or abbreviated form here. Local derivative, and here are our convective derivatives. And this nabla operator is given by this term here. This applies not only to density, as I've shown here, it can apply to temperature, velocities, other fluid properties. You would just simply replace this term here with the property you're interested in. So pressures, for example, would also apply. This is called the substantial derivative operator, and in the general form you can see here. So we would put in density or temperature or whatever in these locations. I just want to give a brief introduction to the Navier-Stokes equations. The name Navier-Stokes equations can apply to either the full set of mass, momentum, and energy conservation equations, or sometimes it's simply used for these momentum equations. But I will quickly show you here the momentum equations. If we look at a control volume, this control volume here, it has a dimensions dx, dy, and dz. And this is using, what I'm explaining here, defining here, is in this non-conservation system. So first of all, in the non-conservation system, it's moving with flow. The element will have surface stresses due to the adjacent liquid. So for example, on this face here, we will have a shear stress tau yz. It's on the negative y face in the x direction, and the area is dx dz. So it gives us our total stress on this face. On the opposite face, we will have the same stress plus a gradient in the stress due to viscous effects. So it would be the change in tau yx with respect to the y direction times dy, and of course dx dz is our complete surface area here. You'll have similar stresses on this face and on the back face round here. On one you simply have these values, and on the other you have a increasing gradient due to viscous effects. On this face you'll have two sets of forces acting. You will have a normal stress and you will have a normal stress plus this gradient. You'll also have a pressure, and on this face an increment in pressure. Now I've only drawn that there for all of the stresses or forces acting in the x direction, but you will also have a similar set of forces acting in this direction, the z direction, and in the y direction. But if we just look at the x direction, we have, through Newton's second law, we have forces equal mass times acceleration. Again, only looking in the x direction. Or in terms of change in momentum, we can have that the force is equal to the mass times the change in velocity over time. So this is the total change in velocity u, x direction, with time. We can resolve the forces in the x direction. So you add all these up in this x direction, cancel out terms, and you will be left with this set of forces. You can add a body force to this. So for example, the most important body force would be gravity. I'm simply adding this term in here. So it will be the component of gravity times the density times the volume. And then lastly, in this equation here, we simply take this expression plus this expression. So we'll have this is equal to this amount here. If you work through that and cancel out terms, you will end up that the density times the change in velocity over time is equal to this set of change in pressure with respect to x, change in stress x with respect to x, and so on. And of course you'll have exactly the same equation as this with different terms in here, of course, in the y and the z directions. This slide summarizes the equations for these different conservation laws. So first of all, equations for the conservation of mass, then conservation of momentum, and then conservation of energy. If we look at mass, first of all, we have a control volume. We know that mass cannot increase or reduce within this volume over time. If it's an incompressible fluid, in this case, density does not change, and our conservation law is given here. So if you think, for example, delta U, delta X is the change in flow in perhaps this direction, if there is an increase, then it will have to be balanced by changes to these other flows, such that the sum of them is always equal to 0 for no increase in mass. If we have density changing with time, so we're talking now about a compressible fluid, this might be the way it's changing with time due to the constitutive law, and then the flows in the three directions have to be given by these relationships, where density is now in the derivative, and the requirement is that the sum of all these terms is equal to 0 for no increase in mass. For conservation of momentum, I introduced this on the previous slide, and there it was expressed in non-conservation form. Now we're converted it here to a conservation form. So the du dt on the previous slide, this was a large D in the du dt, is replaced by this here. This is the local derivative, and here are the convective derivatives. So this is the same as the previous expression, except it's expressed in conservation form. On the right-hand side, we have this also on the previous derivation. And all of these shear stresses are now replaced by these expressions here. Essentially, for a Newtonian fluid, we have this relationship between shear stress and the change in displacement, change in velocity with respect to y. So this is our viscosity. In other words, if we have some velocity here, this is the y direction. Du dy times the viscosity will give me the shear stress. So I can replace all these shear stresses on the previous slide with this relationship, and I end up with this expression here. And we have similar laws for the y direction and the z direction. If we're dealing with a compressible gas or a thermal problem, then you will also have to invoke conservation of energy, and essentially the rate of change in energy inside the control volume has to equal the net flux of heat into the control volume and the rate of work done by body forces and surface forces. So you have to have an energy balance. Now this is not directly the equation that's used. There are much more complex expressions that are applied depending upon whether it's a compressible gas or a thermal problem or both. I haven't made any attempt to derive these equations here. You will find these in the book, for example, by Anderson that I cited on a previous slide. In tutorial 13 of the book, I suggest to students that they write their own little CFD code. I think this is a really useful exercise. It gives you a real feeling of how these codes work, even though this is a very simplified code that you program and perform an analysis with. But nevertheless, it is a very useful exercise, I think. It's based on a publication which I've given up here due to Mark Oakes, and you have the reference here for the download of this paper. As I say, it's on the web, not a problem to get it at all. And what's very nice here is that he describes the theory, and he also provides key sections of the code. So with some cut and paste operations, it's quite easy to build this coding to do the analysis. Now he uses MATLAB for this work. This is a commercial software. If you can also do this, and I've done this with Octave or FreeMat. Both of these codes, or all three of these codes, use the same scripting language. You can perform the analysis perfectly well with Octave and FreeMat. I'm sure these codes are not as certainly they're not as advanced as MATLAB, and the graphics is not quite so good, but it is perfectly possible. If you have no experience of programming, or using these codes, well, if you have no experience of programming, you're going to have to invest quite a bit of time. If you have done programming but maybe not so familiar with MATLAB, like myself, then you will need to look at a few YouTube videos and a little bit of reading. But it's a fairly, for someone with experience on programming, it's a fairly straightforward exercise. The problem he looks at is a classical CFD benchmark study. It's a cavity 1 meter by 1 meter in dimension. There's a lid moving at 1 meter per second in this direction. So the fluid gets a sort of circular motion. There's a lot of further details on this benchmark study given here in this CFD website. Now the method uses finite differences. In this case, there's a grid set up which moves in both directions, and on this grid we perform the analysis. And I first just want to show you some ideas, or give you some ideas, how this finite difference method works. I'm doing this here in the bottom half of this slide for a 1D problem. I think the extension to 2D should be straightforward, and when you come on to look at the paper from Mark Oakes, you'll understand it better. This function I've drawn has the key features of the Navier-Stokes momentum equation. So we've got this d2u dx squared plus u du dx. So in a finite difference scheme, we would split up to a number of points in this direction. And let's say we're interested in finding out what's happening at this particular point. This du dx is equal to this value, or this gradient is equal to this value minus this value divided by this distance. And this is exactly what's given here. So we can get an estimate of this gradient from these actual values. And this u du dx will simply be equal to u times what we've just derived. Now, if we want the rate of change of gradient here, this term, it would be this gradient minus this gradient divided by this distance here. And that is exactly what's given by this equation here. If you look through that, I think it's fairly straightforward to follow. This one, for example, is this gradient minus this gradient divided by this distance. And putting that all together, this expression is given by this here. And that's the basic idea. It's used for pressures, it's used for velocities in the u direction, velocities in the v direction, and in the problem of this cavity, it's done in 2 directions. So these concepts are expressed in 2 different directions. If you do decide to have a go at this problem, there's a few points I just want to raise that make it a little bit tricky, the understanding a little bit tricky. You have to first of all really understand the way in which the grid is set up and the way in which these counters work. So pressures, for example, are stored at the center of each grid or each cell, and these velocities are on the faces. We don't have velocities at the center. U is going in this direction, V is in this direction, Imin is here, and Imax is here, and the x coordinate starts at this point. The y coordinate starts here, and it comes through to Imax plus 1 and Jmax plus 1. What is not clear on this diagram, and perhaps not so obvious immediately in the coding, is that you have another set of points around here. So Imin starts off with a value of 2 because we want an Imin1 for a set of cells that run around the outside. And these cells are necessary to enforce the right boundary conditions on these faces here. Now that's perhaps not so easy to follow, but if you look into the paper, do be aware of this particular point. You will also have to set up certain arrays, understanding what the limits of all this of this mesh is in both directions. Another important point is that we're dealing here with an incompressible liquid, and it's isothermal, so we don't have temperature as a problem. Now we have two sets of equations that will have to be solved. We have the mass conservation equation, and we have the momentum equations. We don't have to worry about energy equations for an incompressible non-thermal problem. So in that respect, it's fairly straightforward. One problem, however, is that we have here three unknowns. We've got the unknowns of U, V, and density appears in here, but we don't have pressure anywhere in these equations. Our three unknowns are actually pressure, velocities U and V. So we can't use these set of equations directly to find our dependent variables. And what is done in effect is that we build another equation. I'm not going to go through that here. Essentially, though, the method is you take the divergence of these equations, which is given here. So we take the differential of this one and the differential with respect to y of this one. So these are our momentum equations in the x and the y direction. That gives you these long expressions here. You add these together and you invoke this in the combined equation. So continuity is imposed through this combined equation. And then you simplify things and you end up with this expression here. Now this is it's a Poisson's equation in terms of pressure. So we now end up with pressure being involved. And this pressure is only a function of derivatives of velocities. In other words, if we use this equation and these equations, we're able to determine for the variables pressure and the velocities. In other words, this new equation, this Poisson's pressure equation, is used as a part of the solution. And what you will find in the solution that Mark Oakes proposes, he does a prediction first of all for the velocities, ignoring these pressure terms, and then he does a corrector for the velocities by working out these pressures. And I think if you can follow what I've said there and you look through the paper, it will make more sense, hopefully. I will show this code, this Octave MATLAB type code that I used at the end of these slides. This is just to show you some of the results I got. This is taken from the Calculix manual. So this analysis has been done by Calculix using a finite volume solution. This is a view of velocities for the flow. You can see the very high shear velocities at the top here, and then you get this flow process. And these results are from the Mark-Oaks finite difference solution. You can see here the velocities that I'm able to create from the Octave software. And then I was able to use a special option called Quiver to make a plot. And this is basically a plot of the velocities u and v in such a way that you can create vector arrows of the direction. And here you can see quite nicely the flow that's occurring. So it gives you some idea of what is possible in terms of post-processing results and what looked like a very good comparison between the two programs. In the last part of this presentation, I will be using OpenFOAM for a simple CFD simulation and post-processing the results with ParaView. I just want, before going on to these analyses and simulations using the Mark-Oaks software and the OpenFOAM, I just want to show you how you install OpenFOAM in FreeCAD. You have to, because it's not already installed, it's something that has to be done. First of all, start up FreeCAD, and you will find, if you were to look, you would find that in the workbenches here, you will not have this CFD OpenFOAM workbench. It has to be added. To do this, you go under Tools and open this up, look down to the add-on manager, and then you can click CFD OpenFOAM workbench. This will then be added to the set of workbenches in here. You have to do a restart to activate it. We also need another option to be added that's used for plotting certain results as the analyses are running. So you have to repeat all of this, but activating the workbench plot. Again, you have to do a restart to activate it. The next thing you have to do is to install OpenFOAM. Now there's different possibilities. I'm only talking for Windows here. On Linux this may be more straightforward, but on Windows there are two possibilities. You can either download a ESI version, which uses a virtual box and various other linking software which runs OpenFOAM, a Linux version of OpenFOAM on Windows, and makes communications. I have tried this and never found it to work. I couldn't get it to work. So what I always use is a version of OpenFOAM that will run natively on Windows. And I find this works perfectly well. The version to download is given in the link here. Take the last version that's available. You also then have to download the ParaView code for post-processing, and that's given with this link here. Again, take the last version. For each of these codes, install them on your PC, the Windows versions. For the OpenFOAM code, you need to note where the directory is that you install it. So you probably can't see it here, but I installed it under Program Files. And it's important to note where the upper directory is. And the ParaView, similarly, install that somewhere on your computer. but you will need to know where that executable is. Once they're installed, you start up OpenFOAM, and under Open Preferences CFD, so these are the tabs available in the main tabs at the top. You will be able to open this particular window here, and this does the installation of these codes, or it does the installation of certain codes, and it also links the executables when you come to do the analyses. The things you have to type in then, or locate, is the directory where OpenFOAM is installed. This is done at the top. I have to just emphasize it's the directory that's needed there. You have to, in this thing, for the ParaView executable, you must locate the executable, not the directory, but the executable. Here you don't do anything. And here, in this part, you have to install the two meshing softwares. So simply click on Install CF Mesh, and it will download this from this SourceForge location on the internet. Once this is complete, and I warn you, it takes a long time. This might take 40-50 minutes to install on a PC. You then install this other meshing software. The location is automatically given here. You don't have to do anything for either of these locations. Just do the install. This will, down here, you'll get lots of information. As I say, it will go on for quite a long time until you get the install completed. Once you've done that, run this dependency checker. It should show you that everything is properly installed, and then you're ready to do analyses. So in the next part of this presentation, I'll show you quickly the coding I did from the publication from Mark Oakes on doing a finite difference CFD analysis. And then after that, I'll move on to do a OpenFOAM simulation using the installation that's done using these operations here. I'm moving on here to show you this CFD code using the finite difference technique proposed by Mark Oakes. I've started Octave and I've loaded up the code that I've programmed. I'll just quickly go through it and show you the main features. First of all, at the top here, we have some initialization of certain information. So for example, here, 30 and 30, this is the grid size, 30 grid at the bottom in the X direction and 30 in the Y direction. Lx and Ly are the sizes of this cavity. Nu is the viscosity, rho density, it's not important, rho actually here. And the time step, I've actually hard programmed it to be 0.018 based upon the formula that's given actually in the paper. These are the limits for Imin, Jmin, Imax and Jmex. That's given on this diagram in the paper, and I also showed you a few slides back. Certain arrays have to be set to 0. All of this is standard MATLAB type programming script. As I say, it's exactly the same as what's used by Octave here or FreeMat. The mesh is created by these commands here. X and Y are the coordinates of the, if you like, the corner points of the grid. XM and YM are the positions at the center of each of the cells. So you can see this 0.5 here and the average of the corner points, if you like. dx and dy is simply the size of the of each grid, depending upon the depending on the grid sizes, and this will be used somewhere within the in the coding for the and it's just the inverse of 1 over dx and 1 over dy. So it's basically initializing information above. Here is the Laplacian operator. This is the Nabla square function in the Poisson's pressure equation. It's done for the complete mesh, and it's done right at the very start because it's constant. It doesn't change during the analysis. You can see here these inverse parameters that I just had mentioned. So we do this one time at the very beginning before the loops, and it will be used in the analysis repeatedly. Down here are the boundary conditions. So this is basically saying that at the top face we have this velocity of 1 in the x direction, in the u direction. So it's the tangential velocity to the top face. Here I set time equal to 0, and then I'm going to do a loop over all of these Navier-Stokes equations, and the time is going to be increased time plus the time step, which I programmed at the very top. Each time these commands here, the semicolon means that nothing is output to the working file as the analysis is continuing, but because I haven't got it here, this value will be printed, and I will be able to see the loops as the analysis progresses from 0 up to 500. Sometimes I use a smaller number here, sometimes larger. This is also a point that's quite important. I've not programmed this in a very smart way. I'm simply going to go 500 loops and hope that within these 500 loops I've reached a steady state solution for the problem. A smarter way could have been to do an indefinite number of loops here and to look, for example, at the norm of the velocities in the x and y direction, or the norm of the pressures. And when these values are hardly changing, when they're less than some kind of a convergence criteria, I could have stopped the analysis then and said, okay, I've got a converged solution, but I'm simply doing it with a fixed number of loops. This is assigning the boundary conditions to the u and the v arrays, which are holding the velocities in the x and the y direction. This is doing the momentum equations for the u direction, the x direction, and this is doing the velocities for the y direction. And here we're using these finite difference approximations at the various grid points. This is without the pressure, so this is what he calls, Mark Oakes calls, the predictor step. This is computing velocities in both directions without pressure included. And in this part of the code is what he calls the corrector step, where the velocities in the u direction and the v direction are corrected for pressures which are now estimated. Finally, down here are some outputs of the information. One thing I was interested in was predicting the total velocity. So I took the over all of the grid points, I took the x, or the u velocity, and the v velocity squared. This is the square symbol, and this is the square root. So I squared them and square rooted them to get a total velocity. This produces an interesting plot, which I've put into an array called UV. And then I start doing the plotting of information. So for example, this is outplotting pressure. This command here sets up a grid. XX, YY. These are my information in the X direction. This is my midpoints in the X direction. This is the midpoints in the Y direction. And this sets up then the grid. And here we do the contour plot using this XX and YY grid. And this is my pressure array. The 30 here means we're going to have 30 contour levels. The plot is going to be put onto a square. So the X size will be the same as the Y size, and there's a title, put pressures. In the second figure, so the previous was the first figure. In the second figure, I'm doing essentially the same, except I'm going to be outputting total velocities, and I'm going to be using this UV array that I have just mentioned. And finally, down here is a rather special option. I'm outputting vector arrows for the U and the V direction. So this gives me a sort of a kind of streamlined visualization of what's happening. The center portion of the cavity, if you remember a few slides back, I mentioned there is an outer region where you have boundary conditions, and there is a central region. I'm putting all of the U and the V velocities into these arrays in the center region, and I will use this XXYY grid for the center region as well. And all of this is put into this plotting option. It's called Quiver, which uses the XX and YY grid with the U velocities here and the V velocity component here. So it produces arrows. They're automatically scaled. This 4.0 is a magnification factor on the arrowhead. I'd rather increase that. The default is 0.9, I think. I'd rather increase that so that you can really see an arrow in some of the areas of the cavity where there's very low velocities. So that's basically it. I'm going to start the analysis. That is done by pressing on this icon up here. Save file and run. Just need to load path for the information. And now it should be running. And under Windows, if I go to Window Command, I will see this time increasing. So I'm going to be doing 500 loops. And hopefully in that 500 loops, we'll be achieving a steady state solution. I hope it's clear that what's going on here is that we have some imposed velocities at the top, and these discretized finite difference equations are spreading these velocities through the mesh. At each time it's solving continuity and momentum equations via this Poisson's pressure equation, and coming up with hopefully a new set of velocities and pressure distribution for the complete cavity. I'm going to just stop the video for a moment while it's running, and I'll come back to it just before it's finishing. So the 500 was reached. It's producing plots of the results, and I'll just separate these now. So we've got up here on the top left, we have the pressure distribution. at the bottom here, figure 2 is the total velocities, and you can see the high velocities along the top here, and then this circular flow. And here is this quiver plot of the velocities showing how the flow is occurring, and then this circular effect here. So that's essentially how it works. I hope that's useful. It is a useful exercise to do. If you have trouble with you're not used to doing this sort of programming, there are plenty of YouTube type videos and other information on the web to get started. But it's hopefully hopefully those videos and what I've just shown you, you'll be able to put this all together. The next thing I will do will be to move on and show you a simulation of a different type of problem using OpenFOAM with results from using ParaView. I'm going to show a OpenFOAM example using OpenFOAM in FreeCAD. I'm going to keep this to a very simple problem. You will find on the web plenty of examples, more complicated examples by people who use this code more often than me. So as I say, I will keep this very simple. First of all, just to make sure, you should have already installed the CFD OpenFOAM code and also this plotting workbench. So just check these are available when you start up FreeCAD. If you had installed those workbenches, you should have also been in this panel here, which is the edit preferences. You will have seen this CFD OpenFOAM, and here you will have given the directory for the OpenFOAM and the location of the executable for ParaView. Also, you will have installed this CF Mesher and this other meshing tool down here. You don't have to come in here again, as I've just done, but it's just make sure that that's all been done. If you want to, you could do the run dependency checker to make sure it's all okay. But every time you come in, as I say, you don't need to go through these steps. So we'll create a new problem. I'm going to resort to the most simple problem of a simple plate with a hole in it, again, just to show the basic steps. So I'll do this in the sketcher. It's probably the easiest. I'll come in here. We'll define the XY plane. I'll specify a rectangle, basically any size. I'll specify that it's a length of 100, and we'll define a height of this maybe of 50. I'm going to put a hole in the center, so we need this option. Again, I don't worry about the dimensions at this stage. Right key just to stop that operation, then we come on here and then on that, and then I can specify a dimension here. Let's do it 10, for example. Yeah, that should be okay. Now I want to right mouse key just to stop that, use this operation, this constraint between here and here, to specify that that distance is 50. And we'll do the same for a vertical constraint between here and here to specify that that distance is 25. So with those different operations, we've got a plate 100 by 50 with a hole in the center that's radius 10. That's fine. We'll close this. We'll come through to the part workbench. we'll use the extrude operator here with, let's just say 4 millimeters. Apply. Okay. So we've got our structure, our component, looks fine. We'll now start up the CFD OpenFOAM workbench. We specify a container, and within this container I've got certain information to define. So for example, if we go into the physics model here, I'm going to use steady state, single phase, incompressible, and viscous. In the fluid properties, I'm going to specify this to be water. Again, note the units used. If you want to change anything for any reason, then change it, obeying whatever units are here. When the data set is written out to OpenFOAM, there will be conversions made to whatever consistent set that OpenFOAM is using. So we'll say OK there. I'm going to define now the boundary conditions. That's done with this icon here. I'll start off by defining that all the surfaces, so I have to click them all, and that's done by holding down the Shift key and clicking on them. Of course, you've got to rotate the component round to be able to do the selection. So we've got the 4 now. I'm going to say that this is a wall, and let's say it's a no slip. Well, let's use partial slip. Slip ratio now. To be frank, I do not know what these sort of parameters are. So the best thing, I'll define it as a slip, perfectly frictionless part, surfaces. That's okay. We now define the inlet, which must be this surface here. Again, we'll come in here, inlet. I'm going to select it, and I'm going to define a velocity. Let's use something like 200 millimeters per second. So that should be okay. We'll have to move this around now. I need to select the outlet, again using the same icon, outlet. That's okay. And I'm going to leave it at a pressure of 0. Could be 1 atmosphere, but I leave it like that. And finally, we need to do something for this in the center here, the hole. Again, I'll select a wall. Colors are a bit unfortunate here. Selected there, no slip. Let's use slip again. It's just to show you the operations. Okay, we've got that defined now. Initialize fields. I'm going to use potential for velocities and potential also for the pressures. And finally, we have to mesh it. That is using, so we click on the extrude, and then this flag here, this icon. Write the mesh, run the mesher. I'm using this mesher down here, CF mesher that's been installed. We'll have a look what sort of mesh it develops. It's given a 1.6 here. By default, for whatever reason. We can change that if we don't like the mesh. The meshing's finished, so we load the mesh here and have a look. And actually this mesh is really not too bad. For a CFD analysis we could use finer, so let me just take a slightly different mesh. You have to, let's clear the mesh, write the mesh, run the mesh again. If you do make changes, you've got to do this write operation and then this run operation again. It shouldn't take too long for this simple part. Load mesh surface. So something rather similar, very fine mesh, but I think we'll use that, possibly a little too fine. You can start up ParaView here in this icon, and then you have a chance to have a better look at this mesh. In this case it won't make too much difference. I'll start this, but there can be other components with more complicated meshes where it can be useful to start up ParaView. Have a look at that, make sure you're happy with it. Yeah, it looks fine. I'm going to close this again. We'll close here means that the mesh has been saved. And basically we're ready to do the analysis. Everything's been defined, the mesh has been defined, and all the boundary conditions defined. So we double click on that. We write out the data set and we run the data set. Now this should open, well, it's opened the plotting, but it should start plotting out the residuals for the velocities and the pressures. You can see them here. We're not involved with temperature or anything, and these residuals are reducing. It will by default, but you can change the default, it will go for 2000 iterations. But usually once you've done 400 or 500 and they've reduced to a reasonably low constant value, you can start looking at the results. So I'll let this just run for a little bit. I'll press the video stop a moment. So the analysis is progressing quite nicely. All these values have become very steady. Obviously that's not necessary to wait any further to look at results. We can start up ParaView directly from this panel here. The analysis will continue to run, but you wouldn't expect the results to change hardly at all now. So ParaView started, and here's our component. This is a contour plot of pressure. We can look at velocity. Gives you some idea of the effect with time for velocities. We can look at streamlines, probably the most useful. It's this option here. There's two ways of doing this. It generates a line, which is a bit difficult in this case to see, and you put a line through the part, and then along this it will look at the flow, and it will create a set of streamlines which will then be populated through the part. Let's you have to apply to start that. It's just run through it and looks a little bit strange, but there will be streamlines obviously in here, but it's missed those off at the moment. The better way perhaps is to, instead of using the line option as a point cloud, and you can locate this in one area that you're interested in. So for example, this could be the inlet of some tube or something. So you click on there, say apply, and then you can see what happens with the flow in this region. If we took another region, imagine down here, say apply, we can see again the flow. And you can investigate different regions, as it were. We can, there are other options to make these lines, the density is different, the size of the lines different, and so on. But you will find videos on the web on that. Just going back to this, just to look at the velocities. This is velocity here. We've got an input velocity. I think it was, I've forgotten now, 200 was it? But you can see how it does increase the velocity around here, and then we've got these very low velocities in the wake of the just directly in front and behind the tube. You can do section cuts. It's not so interesting with this structure, but there are possibilities for section cuts. The best really is to just experiment with using ParaView to see different visualization options. I think that covers basically all I wanted to. It's a very simple, trivial problem perhaps, but it does show the principles of how you set up and perform a OpenFOAM analysis. So this presentation on computational fluid dynamics kind of wrapped up the course that I wanted to present. I've gone through 7 videos, one on each chapter, listing there the what I felt were the main topics important for finite element analysis, and then the 4 tutorials, the first 3 on finite element analysis and the last one on CFD analysis. I would like to just make a special thanks to all those people and companies who have developed these open source softwares. It really is an enormous task, and very generous of them to make these available so that people, students can experiment. Special thanks, as I say, to the FreeCAD and Calculix people, to FreeMat and Octave, and also to the OpenFOAM, Blue Cape and ParaView software, the individuals. As I say, it is really marvelous that they make these available. I know how difficult it can be developing software myself. I've had a go, and it's a rather thankless task at times. You only ever hear something when things go wrong. So really, thank you to everyone there. If you have found the course useful, please maybe put some likes or subscribes on the various parts of the course. It would be a shame if it all kind of disappears. And I just want to wish you all the very best for the future, and good luck with your finite element analysis work.